So I'm Martha White. I'm an assistant professor in computer science, and I work in machine learning. And today I want to tell you just a brief overview of my passion for autonomous agents, and particularly an approach that I think is really important for autonomous agents. It's called reinforcement learning. So let me tell you a little bit about reinforcement learning and kind of get into the mindset of how I'm approaching autonomous agents. So, you got it. You know what? I'll just hold this to my face. Is that all right? Can you hear me now? Great. Okay, so let me tell you a little bit about why reinforcement learning is a really great approach to doing something like autonomous agents and having adaptive learning. So generally, we would like to learn in unknown or partially observable environments, and in that case, we're thinking about a setting where we have some agent that only gets some limited sensor information, and we would still like it to be able to learn something about its environment. We don't want to assume any kind of a priori information, so we don't want to assume, say, dynamics models. We want the agent to learn as much as it can from scratch from the environment. And so typically it's only going to have some observations that it's getting in and some scalar feedback from the environment that says maybe an action was good or bad. So I have this little video here so you can kind of put yourself in the mindset of what an agent sees within reinforcement learning for this type of paradigm for adaptive agents. So here, for example, you might have this little grid world. There's all these blue walls, and the agent is a little black dot at the bottom, and it's trying to get to this goal at the top. It has no idea what this map looks like. All it's going to get on each step is a -1 until it gets to the goal, and then it's going to get a positive reward. So let me just play this so you can see how it looks. If I knew where play was, there we are. Oh, okay, great. So here it's only information it's getting is immediately the XY position that it is in and the coordinates that it's at, and it doesn't get to see anything else in its environment. So you can kind of imagine this is a very limited observation space, and now it's going to start exploring its environment. Again, getting -1 each time it hasn't reached the goal. So as it gets to the goal, it's going to start seeing that is a good path to go, and it's going to start backing up positive value. But it's not going to immediately go back to the goal because it's still going to try to explore the environment a little bit more and make sure that it's confident that that's a good place to go. So this is generally the kind of setting that we're imagining in reinforcement learning, that the agent has to build up a model of its environment, be confident that it's learned a good solution, but only with a very limited amount of information. So the key challenges for me here are that I really like to tackle in this area. You can imagine there's a lot of different problems when it comes to control and such a limited amount of information given to the agent, is really how are we going to effectively explore our environment and be confident that we learned an optimal policy. How are we going to learn effective models of our environment? So here this is a function approximation question. And also, how are we going to have efficient algorithms for this continual learning setting? So we have a stream of data that's constantly coming in. It's going to be high dimensional. There's going to be lots and lots of samples, and we want to make sure that we're actually able to have the agent make decisions efficiently and use that data efficiently. So for example, for function approximations, one of the areas that I've been looking at a little bit is how can we learn neural network models that we can confidently say something about the solution that we're actually going to get from those neural networks. In terms of efficient algorithms, there might be something like how are we going to process samples one at a time in something like stochastic gradient descent, and still say something about what our solution quality is going to look like. Okay, so these are some of the research challenges that I'm really interested in, but you can also imagine that there's many domains that this type of approach can be applied to. So I want to give you an idea of where you might actually care about reinforcement learning being used. The grid world isn't really an example of a realistic domain that someone might want to use reinforcement learning, but reinforcement learning is actually being used in interesting areas. So one area at the school right now is this thing called precision medicine. It is one of these grand challenges. And one of the things you could imagine doing for something like precision medicine is taking these really big logs of doctor-patient interaction and then trying to learn decision-making policies from those logs to have an agent that makes suggestions from a big vector, say, of information about a patient, suggesting, let's say, what a potential treatment decision could be. So this is a big challenge domain to learn, and we have these high-dimensional inputs, we have lots and lots of samples, and we want to try to leverage some of the algorithms in reinforcement learning to learn this domain. But there's lots of other domains that it is either could be used for or is currently being used for. An example is article recommendation. Something like reinforcement learning is used by companies like Google, where there's only a very limited scalar feedback. Something like a user clicked something, or they did not click something, or they did buy something, or they did not buy something. And you have all this information about that user, and now you'd like to be able to determine what kinds of things should you recommend next. So your action is what kinds of recommendations could you make. So my goal really behind this is to kind of give you an idea about what reinforced learning is, so some of the research challenges, and also why you might be interested in using reinforced learning in your area. Thank you.